So, first of all, let me say that I want to dedicate this presentation to my co-researcher, Cesar Martinez Hernandez, whose life was sadly taken away from him by COVID-19 on December 15th of last year. This presentation would not be possible were it not for his essential contributions to this study. By way of introduction, I want to say first that in the numerical algebraic world of school mathematics, equivalence has two faces, one computational and the other structural. And in primary school, much of the past research has focused on expanding students' views of the equal sign, and the emphasis has either been on students' use of the equal sign as an operator symbol or relationally, and with the passage from one to the other. However, the multifaceted structural aspects of equivalence within a numerical setting remain largely unstudied, despite their relevance for later work in school algebra and the importance of beginning to develop such algebraic thinking at the primary levels of schooling. So the present study, which was carried out with 6th grade students 10 to 12 years of age in a public school in Mexico, aimed at partially filling this gap. So the structure of my presentation is as follows. First, there will be a brief review of the theoretical and empirical literature on equivalence, on structure, and on properties. The second part will deal with the research study itself, starting with the research question, going through the participants' procedures and design, and then into the unfolding of the study, where 6 phases were noted in the student's shift from the computational to the structural. The third part of the presentation will focus on discussion, the role of the interviewer's interventions, the role played by the decomposing property of the addition structure in the student's evolution, the role of students' number sense and computational knowledge in making the transition to the structural, and then finally a closing remark on structural versus computational views of equivalence in later algebra. First, equivalence. We have traces of the notion of equivalence from the earliest days, even from the days of Euclid, and going through to Hilbert and more recently. However, equivalence took a rather winding path to arrive at its modern definition as formulated in the 1940s. An equivalence relation is a binary relation that is reflexive, symmetric, and transitive. The relation is equal to is the canonical example of an equivalence relation, where for any objects A, B, and C, A equals A, the reflexive property. If A equals B, then B equals A, the symmetric property. And if A equals B and B equals C, then A equals C, transitive. Equality is a relationship between two quantities, or more generally, two mathematical expressions, asserting either that the quantities have the same value, or that the expressions represent the same mathematical object, or that an object is being defined. I'm having trouble advancing my... Okay. First of all, equivalence in the numerical world. A computational dimension. This dimension arises from the above definition where two quantities have the same value, as in 5 plus 9 plus 3 is equal to 10 plus 7 is true because both sides evaluate to 17. The structural dimension arises from the same definition of equivalence, but without evaluating, and capitalizes on the reflexive property, where A equals A, with A being a mathematical expression, as in 5 plus 9 plus 3 is equal to 5 plus 9 plus 3, where the structure of the non-computed sum of each side of the initial equality is reflected in the same decomposition on the two sides of the transformed equality, and whereby the truth value of the equality statement is visibly obvious without computing. Historically, it's interesting that Freudenthal, for one, did not invoke the above 1940s definition of equivalence. Instead, he characterized equivalence in the mid-1960s as follows. An equivalence relation is a relation that possesses the following two properties. A is equivalent to A, and if B is equivalent to A and C is equivalent to A, then C is equivalent to B, which he referred to as transitivity. Freudenthal, moreover, stipulated that the symmetric property is a consequence of transitivity and reflexivity rather than being a defining property. That is, if A is equivalent to B and B is equivalent to B, then B must also be equivalent to A. He held that symmetry is embedded in the situation and is therefore implicit. In his later writings, however, he addressed more directly the aspect of symmetry. Nonetheless, our position is that symmetry is vital to understanding and expressing the equivalence of expressions in numerical equalities in a structural way. Symmetry can be applied to 3 plus 4 equals 7, for example, so as to yield 7 is equal to 3 plus 4. That is, 7 can be decomposed into 3 plus 4 or any of its other additive components. As I will argue later, this property of decomposition is central to the generating of equivalent numerical expressions. Unlike equivalence, structure is not a well-defined term, and there is wide divergence in the mathematics education community on its meaning. For Mason and his co-authors, the structural is closely intertwined both with the general and with attending to properties. As he and his co-authors have written, we take mathematical structure to mean the identification of general properties which are instantiated in particular situations as relationships between elements. When a relationship is seen as instantiation of a property, the relation becomes part of a structure. Structural appreciation lies in the sense of generality, which in turn is based on basic properties of arithmetic, such as commutativity, associativity, and so on. However, we wish to take a broader perspective on structure and structurings, and to do so, we turn to Freudenthal, who has said that the system of whole numbers constitutes an order structure where addition can be derived from the order in the structure, such that for each pair of numbers, a third its sum can be assigned. The relations of this system are of the form A plus B equals C, which he refers to as an addition structure. He has also described in a similar fashion the multiplicative structure. But it's quite important to note that Freudenthal emphasizes multiple means of structuring and properties that can be characterized in a way that is not restricted to their axiomatic formulation within the basic properties of arithmetic. For example, we can have the successor property, the sum of consecutive odd numbers property, and so on. In order to spend just a few seconds here on the importance of a property-based structuring activity, we note that high school algebra involves working with generalized forms. But this activity also requires the ability to see structure in these forms and to re-express these generalized forms with equivalent structures. In other words, algebra is not just about generalizing. Algebra is also about dealing with structure. Hodge and Dreyfus, in their research, stress precisely this aspect when they describe structure sense as including the ability to divide an entity into substructures. However, they found such structuring ability to be weak in the high schoolers they studied. Even more so, the students' ability to draw upon underlying properties to form equivalent structures. Linchevsky and Livney, who were the first ones to use the term structure sense, draw our attention to young students' difficulties with using knowledge of arithmetic structures at the early stages of learning algebra. They suggest that instruction in arithmetic be designed to foster the development of structure sense by providing experiences with equivalent structures of expressions and with their decomposition and recomposition. In line with Freudenthal, then properties can be characterized in a manner that is not restricted to the axiomatic formulation within the basic properties of arithmetic. The discussion of properties related to structural thinking with numbers and numerical operations can be broadened. This leads us to consider decomposing, composing, and recomposing also as properties that are tied to the order, addition, and multiplicative structures. The use of these properties is anchored in the symmetric property of equality. That is, symmetry allows for the rewriting of the addition fact of, say, 5 plus 7 equals 12, as 12 equals 5 plus 7. In other words, 5 plus 7 can be composed into 12, and 12 decomposed into 5 plus 7, or any of its other combinations. With respect to some of the related empirical research, as I mentioned earlier, much of this research has focused on the use of the equal sign, the operator versus the relational view of the equal sign. The tasks that are used in much of this equal sign research have involved true-false equalities, where students are asked to state their truth value, and open sentences to determine which number will make the sentence true. It has also been found that by about the 5th grade, most students can accept equalities with operations on both sides. But very little research on the equal sign and equivalence has included the activity of generating numerical equalities equivalent to given equalities, and the role played by decomposing, composing, and recomposing. Notice that the term I'm using is that of equalities rather than equations. We use the term equalities when the components on both sides of the equal sign are purely numerical, and reserve the term equation for whenever there is an unknown or variables involved on one or both sides of the equal sign. One related exception to this very little amount of research is the work of Elizabeth Warren, who found that only 5% of the 672 7th and 8th graders she tested responded that there was an unlimited number of possibilities for the question, write other sums that add to 23. How many can you write? And fully 1/3 of the students failed to respond to the question in any way. So to summarize, with respect to equivalence, thinking structurally about and representing number and numerical operations can be done in such a way that decisions about equivalence can be made without resorting to computing, but instead structurally by relating to the structure of number and its properties. With respect to structure and structuring, our broadening of perspective leads to the following properties in generating equivalent numerical equalities. In particular, the decomposition and composition properties of the order and addition structures derived from the symmetric property of equality. Also, We will speak about the common form property of equivalence. That is, for a pair of expressions, converting either or both expressions into a common form can be used to indicate equivalence, this being based on the reflexive and transitive properties of equality. And from the empirical research, we note that little research has focused on the nature of the structural thinking involved in primary school students generating equivalent numerical equalities. So the research question of our study was as follows. What are the ways in which a structural form of thinking unfolds during the implementation of tasks related to the generation of equivalent numerical equalities by students who are nearing the end of their primary schooling? Now, the second part, dealing with the research study itself. 6 students from the 6th grade of a public community school in Mexico participated in the first part of the study, which was conducted when the students were halfway through their last year of primary school. The second part of the study took place when the students were finishing their last year, that is, the end of the 6th grade. None of the students had had any prior experience with structural activity involving equalities, or in particular, with generating equivalent numerical equalities, but they had been exposed to equalities with numerical terms on both sides of the equal sign. The data collection technique was that of the group interview, where the students first worked individually on a given task question or set of questions. This was followed by an interviewer-orchestrated discussion segment where the students would share their responses with the rest of the group. During this group sharing, the interviewer, who was Dr. Cesar Martinez, would probe their thinking by asking for clarification, or he might also pose additional questions. The data from part 1 was based on 3 sessions, 1 session per task set, with sessions lasting about 60 minutes each in one of the rooms of the school. All 6 students participated in each of the 3 sessions. The data from part 2, based on 1 session that lasted about 60 minutes and involved 3 of the 6 original students. The 3 who were probably the most vocal and who had the most to contribute during part 1. The data sources for both parts of the study include the individual students' written worksheets, videotaped footage of the interviewer interacting with the group of students and the recording of all their verbalizations, and the researchers' field notes. All interactions and task sets were in the Spanish language. For part 1 of the study, 3 task sets were designed to explore students' strategies related to structure within the equivalence of expressions and equalities. The first 2 task sets did not include the equal sign. Task set 3 involved the equal sign in numeric equality statements and included 2 or more numerical terms on each side. The equalities that were used in task set 3 were as follows. This one, this one, this one. This was the 4th one, as well as the non-equality. This 3rd task set consisted of 2 types of questions. One asking students whether a given equality statement was true and to explain why, and the other to rewrite the true equalities in another way so as to show they were true. Due to the computational nature of the results obtained for task set 3 in part 1, a new task set 4, was designed for part 2. This task set involved true equalities of equivalent expressions. These were the 3 equalities that form the basis for task set 4. However, the task instructions specifically requested that the students not calculate the total of each side in order to show that the equality was true, and then to explain their reasoning. The last question of the task set focused on generalizing the main strategy that they had been using throughout the task set. With respect now to the unfolding of the study, student structural thinking was found to evolve through the following 6 phases in their generation of equivalent numerical equalities. The first phase, computation without decomposition. The second phase, computation with unrelated decomposition of each side. The third phase, ad hoc decomposition of one side and copying the decomposed expression over to the other side. The fourth phase, decomposition of both sides into a third common form. Phase 5, decomposition with some composition of one side so as to match the other side of the initial equality. And phase 6, the expressing of structural approaches in a general way. So now we will look briefly at each of the 6 phases. The first phase. In the first 2 task sets, which did not involve the equal sign, there was a very strong evocation of computational views. For the first task, can the number 7 be written from the numbers 6 and 1? If so, how? The students answered affirmatively and explained their thinking by means of a computation involving the property of composing the addends. For task set 3, where all of the questions included the equal sign and involved, for some equalities, smaller numbers, and for others, larger numbers, the students could accept without hesitation equalities in the form of A plus B is equal to C plus D, and justified their truth or falsity by calculating the result on each side and stating that an equality was true because we get the same result. Notice in the example of student 3's work shown here, when asked to observe the given equality and to respond as to whether it was true or false, in order to respond, we see that the student added up the numbers on the left side to get a total of 609 and added up the numbers on the right side, got the same total, and therefore concluded that it was true. And to explain in his own words, he said, because we get the same result. The second phase, computation with unrelated decomposition of each side. Each of the tasks in task set 3 also included the question, in what other way could you rewrite the given equality? Now, keep in mind that the students had already computed the total of each side. Nevertheless, they were still able to generate alternative forms of the equality by independently decomposing each side. Here we have the work of student 1, where the left side was decomposed this way, the right side was decomposed this way. Student 3, who had also computed the total for each side, proposed for his decomposition of the left side rather a decomposition of the total and a different decomposition of the same total that he found for the other side. Notice, in both cases, there's no inclination to re-express the equalities so that both sides of the new equalities looked alike. In the third phase, when the students were brought together for the second part of the study, task set 4 requested that they show the truth value of each of the given equalities, but this time without first calculating the total of each side. There were initially looks of puzzlement among the students as if to say, what other way is there other than finding the total of each side of the given equality? So some prompting on the part of the interviewer became necessary. Here's an extract from the beginning of this prompting, where the interviewer asked, would there be a way to write also, referring to this given equality, but using these same numbers? So student 3 volunteers. Yes, he suggests 5 plus 5 plus 5 plus 2, which the interviewer wrote on the board underneath the left side of the given equality. And the interviewer says, okay, student 3 says that this could be written as 5 plus 5 plus 2. Is this okay? Student 1 and student 2 both say yes. So the interviewer says this, referring to the right side of the given equality. In which other way can this be rewritten? Can it be expressed this way? Student 3 says yes. So the interviewer writes the corresponding expression on the right side. And student 2 and student 1 say it gives the same. However, it was not yet certain whether or not that right side that had been proposed had been decomposed or simply recopied by the students on their sheets over to the right-hand side. So this issue was tested with the next equality, which involved larger numbers. We were able to confirm that the decomposition that the students had carried out was merely copied to the other side of the equality. Student 2, for example, proposed transforming the left side of this equality as follows. When she subsequently copied this over to the right side and was asked by the interviewer how the new right side related to the initial right side, she was unable to do so. So eventually she rewrote the left side differently, but in such a way that she could reconcile it with the right side of the initial equality. The interviewer decided at this point to return to the prior example that they had generated and asked about the need or not to calculate the total of each side when they generated a second equivalent equality such as this one. He said, seeing it this way, is it necessary to add up in order to decide if the equality is true? Would you still add, or is the addition no longer necessary? What is this and this expression like? Student 2, the same. Student 3, the same. Then is it necessary to add? Oh, no. If it's the same, obviously it will give the same. If the expression is the same, it will be equal. It will give the same. Now to the fourth phase, where both sides were decomposed into a third common form. The evolution towards a genuine decomposition of both sides of the initial equality, so as to obtain an equivalent second equality, proceeded. As we see, student 3 here decomposed the left side as follows, wrote his equality, and the right side in this way. So this decomposition of the right side was guided by the decomposition that he had carried out on the left side. His work suggested the search for a different third common form, where you write by decomposing both sides so as to show that both sides are the same, even if the order may be different. This strategy differs from the previous ad hoc decomposition strategy in that both sides are genuinely decomposed and the decomposition of the second side is guided by the first so as to obtain the same common form. The last step in the consolidation of the common form strategy was provoked when the interviewer asked if it would be possible to rewrite the equality, this one, in such a way that the common form would be the same as one of the two sides of the initial equality. Student 3 simultaneously related both sides of the initial equality by composing 8 plus 2 into 10 and decomposing the 16 into 12 plus 4. if we take one more quick look at this evolution from phase 3 through to phase 5. In phase 3, the ad hoc decomposition and copying involved here decomposing side A into form C, copying it over to the right side, and then testing to see if it was equivalent to the expression on the right side. In phase 4, decomposition into a third common form involved decomposing side A into C, and guided by this decomposition, using the same decomposition of side B into C. And the fifth phase, decomposition of one side so as to match the other, using this generic example. We see that 530 was decomposed into 300 plus 230, and then the 230 was reassociated with the 200 so as to yield the same expression on the left side as the expression on the initial right side. And phase 6, expressing structural approaches in a general way. The last question asked, what should be done regardless of the numbers involved in the equality and without calculating the total of each side to show that the equality is true? Interviewer asked student 1, what did you write? She wrote, I wrote that it must be simplified, that we must simplify the numbers or convert them in a different way, but they should be the same. While somewhat ambiguous, we inferred that she meant that the numerical value would remain invisibly the same. This was clarified a little later when she offered an alternative transformation that would lead to matching the other side, thereby referring to the idea of visible sameness between the left side and the right side. So by means of the generic examples, and they did tend to use generic examples to talk about what they meant, they conveyed in a fairly general manner, even with somewhat imprecise language, the dual aspect of matching both sides of the equality and doing this matching in such a way so as to safeguard the uncalculated values of each side in a process of generating equalities that were structurally equivalent to a given equality. If we use the lens of sameness, we can talk about the invisible and visible sameness that the students referred to when we interpret their generalized strategies. In their explanations, there was an emphasis on the aspect of invisible sameness between the original expressions of the initial equality and their transformed versions that were obtained through decomposition and recomposition. They stressed several times that each of these transformations gives the same. This invisible sameness reflected the top-down vertical equivalence of one numerical equality with the other. On the other hand, the aspect of visible sameness was verbalized in terms of their having created an alternative form of the given equality where the two sides matched each other. That is, a visible sameness that reflected the left side and right side equivalence, the horizontal equivalence of one side of the equality with the other. So the elementary notion of sameness in terms of computational results with which they had begun the study had developed into the subtler dual notion of sameness that involved the coordination of two facets, that of visibility and also invisibility, both facets relying primarily on the use of the decomposing property of the addition structure. Now we move to the discussion, where we look first at the role of the interviewer's interventions in the student's development of the structural dimension of equivalence for numerical equalities, the role played by the decomposing property, the role of students' number sense, and a closing remark on structural versus computational views of equivalence in later high school algebra. The interviewer's prompts were crucial to enabling students' evolution, especially during the third phase, with its 5 key interviewer interventions. The first was the request to show the truth value of each of the equalities, but without calculating the total for each side. This was supplemented by the suggestion implicit in the interviewer's follow-up question that asked if the students could find a way to rewrite the given equality, but based on the numbers that were in the equality. When students then decomposed one of the 2 expressions of the given equality, they were asked, where do these decomposed numbers come from? Since the students then simply recopied the decomposed expression over to the other side in order to complete the transformed equality, they were asked to justify their recopied expression. That is, to relate explicitly the recopied expression to the corresponding expression of the initial equality. And the 5th prompt involved eliciting the awareness that the students no longer needed to total each side of an equality in order to determine its truth value. From this third phase onward, the realization that equivalence could be shown by converting either or both expressions of an equality into a common form was actualized and came to be expressed in a generalized, albeit generic, manner. The teacher was crucial, the teacher being the interviewer in this case. Even well-designed tasks in and of themselves do not foster the growth of algebraic thought. While the point of departure for the group interactions was the tasks themselves, which the students had worked on before sharing their approaches, tasks cannot be separated from the way in which the interviewer posed additional queries about the tasks and their responses, and the way in which he verbally extended the actual written tasks. Furthermore, structure sense does not develop naturally in primary school students. As emphasized by Bass and Ball, it depends on teachers who can hear the mathematics in students' talk, who can shape and steer problems to a productive point. That is, it needs the thoughtful intervention of a knowledgeable teacher, or in this case, interviewer. What was the role played by the decomposing property in students' evolution? Students' decompositions showed certain numerical structures. Note the way student 1 decomposed this expression this way. Or in phase 3, student 3 decomposed 10 plus 7 as follows. And in phase 3, student 2 decomposed this expression as follows. Note the basic units of place value, doubles, and halving. So during their primary schooling, students had clearly developed a fairly strong number sense in the growing of their computational knowledge. As expected, they could compute forward, but they could also work backwards by breaking up numbers into their principal structural parts. Which brings us to the role of students' number sense and the computational knowledge in making the transition to the structural. Baroudi and Ginsberg have argued for not eliminating children's initial tendencies to compute in order to establish equality and to make sense of the equal sign, stating that this knowledge is vital to making sense of later approaches towards structural conceptions. Knowledge of numerical structure and aspects of computation underpin the development of students' structural sense for equivalent equalities. And this resonates too with Svart's theory of operational structural duality, where she has stated, from the developmental point of view, operational conceptions precede structural. But later on in secondary school algebra, the structural alone will not suffice. When students encounter algebraic equations that represent rational functions, a property-based structural perspective will not be sufficient. A numeric perspective will also be required. That is, domain needs to be accounted for when considering the equivalence between, for example, the expression x minus 2 over x squared minus 2x, and its structurally transformed version, 1 over x. So it may seem ironic that the development of a structural view of equivalence at the primary school level involves some dampening down of the usage of the computational, but that both the computational and the structural dimensions of equivalence will be needed for part of the later study of algebra. So to conclude, we can look upon equivalence as a dance between the structural and the computational. Property-based decomposition of algebraic expressions is central to the structural aspects of algebraic equation solving in secondary school. Top-down equivalence of the successive equations in the equation solving chain is a crucial idea, one where, as Freudenthal reminds us, the thing that remains equal at the various steps is not a numerical, that is the total of each side, but a truth value. Of course, further refinements to the structural and computational dimensions of equivalence will be necessary when students learn the structural property that performing the same operation on both sides does not change the truth value of the equation, as well as when encountering equations that represent functional situations where some computational testing will need to be done. But that is a whole other story. Our designed approach to generating numerical equalities is clearly a first step in the dance of equivalence, and one where within this approach, the structural takes the lead over the computational. I thank you.
Thank you so much, Carolyn. Do we have any questions?
I have a question, please.
Okay, Carlos.
Professor Kieran, thank
Yes.
you for your intervention. Please, the research somehow showed that some students prefer one of the two-dimension computational or structural to understand expression. They prefer one, or they take the two dimension.
Yes, to answer your question, first of all, I would like to just stop sharing my screen. So how do I do that?
With stop.
With the green button.
Okay, one minute. I'll try to.
At the bottom.
Okay, at the bottom.
Mm-hmm.
Okay, all right, good. Yes, you were asking whether students preferred one or the other. In the first two phases, as you could see, all the students preferred computers. The only way they knew how to determine that inequality was true. They computed both sides. And the object of the teaching intervention was to see how they might evolve towards a structural perspective on equivalence and stop computing and instead decompose both sides in such a way that they would obtain an equality that had left and right side being identical. Does that answer your question?
Thank you. Yeah.
Randy has a question as well. Randy. Primary.
I'm sorry, that was kind of broken up. I couldn't hear all of it.
Yes. I will explain that Randy is interested in students that have, what is it called, attention deficiency. and hyperactivity.
TDA is
Yes.
TDA.
So you're wondering whether the same approach would work or whether it would need to be adapted for such students?
¿Quieres decirlo en español, Randy? Y te ayudamos. Bueno,
Okay.
recuerde, Randy, que eran solamente 6 estudiantes. Yes, he was asking if you had any opportunity to analyze these approaches with students that have
No, we have not carried out any of our research, and I have not done any research in my last umpteen years with students with such learning difficulties. Attention deficit disorder, no.
hyperactivity.
Yeah, hyperactivity, no. Of course, in any classroom situation, I think you're going to have students who have some degree of inattention. But what we did find was that with the group interview format, after the students had worked on the problems themselves, the sharing among themselves was quite effective because they were able to learn from each other. The teacher, the interviewer, was able to ask additional questions. And each of the students who participated in this small group, each of them was keen to show what he or she could do and what he or she had picked up from his or her neighbors' comments. So I can only suppose that it might work in a situation where there are more learning problems, but I can't say for sure.
Carolyn, you use the term phases, about the 6 phases of decomposition and recomposition. Do you think of them as phases that you have to pass through? So for you to be in phase 5, you must have been in phases 1 to 4 before. So how do you conceptualize the phase term here?
All right. What is interesting about conducting research in Mexico as opposed to Quebec, for example, is that teachers have in Quebec the tendency to move very quickly from one phase to another. And in the process, they may leave some students behind. Whereas we found doing our research in Mexico, the teachers were much more careful to go more slowly, to make explicit these different phases that became evident in this particular study, so that in the end, one had a better feeling that the students, all of the ones who were in the group, had all been able to enjoy going through these very explicit phases. It's probably not necessary for some. Perhaps student 3, who seemed to be the quickest of those last 3 students in part 2 of the study, was ready to go from phase 1 to phase 6, probably in a few minutes, but the other 2 were not. And the way in which the interviewer conducted the group sessions was such that the student who was the quickest still went along and contributed, and in the process brought the other 2 in that group to where we think he might have been much earlier.
So I was wondering, you have done this with natural number arithmetic, so not integers at large or not fractions and things like that. Have you considered generalizing the domain into those number domains to see whether other features would arise?
Yes, that was the plan. The plan was to extend the number domains and the operations as well. However, the planned study has come to an abrupt end because my collaborator, as I mentioned in the beginning, passed away in December. In fact, sadly, on Tuesday of this coming week, he would have been celebrating just his 40th birthday. So it's really sad to know what COVID has done to our research community. Perhaps in another life I shall. I'm not sure that I will in this life.
Thank you, Carolyn. Are there any other questions? If not, Mauricio, do you want to give us our instructions? What are we to do now?
Doctora, me dice en español que si tengo que algunas instrucciones que
¿Quieres dar las instrucciones sobre qué debemos hacer ahorita?
Doctora, pues ya terminó esta conferencia, pues ahora que sigue a las...
Creo que...
Un receso, doctora, un receso, y luego nos reunimos nuevamente en la tarde, sí, señora.
That's right. Yeah, so now we will have a recess for lunch, and we will see you again in the afternoon. Entonces, creo que los otros entendieron a Mauricio. Once again, my thanks to you, Carolyn. It was very nice. It has been nice to see you in our seminars on Wednesday and very nice to hear you in the symposium. Thank you very much.
Thank you to all of you for your patience.
Okay, we'll see you. Yes, exactly. We'll
See you in an hour.
Gracias, doctora.
Thank you. Bye-bye.